The second lecture by Bob Coecke from Cambridge Quantum Computing. Today he is going to talk about quantum NLP and quantum AI. Bob, please start.
Thank you. I don't know what this blue thing is doing on my screen. It's kind of weird, but I don't think it's going to be very important. So, as it was yesterday, I talked about what was more sort of coming from a logic, conceptual point of view, a new way to think about quantum mechanics compositionally, like focusing on the tensor product rather than the other structures like addition and all that. So this kind of fits this in what I would call a new quantum logic. Now, what I'm going to talk today is that this new quantum logic, so to say, is not only specific to quantum, but we find it everywhere around us. In this particular case today, I will specifically look at language, natural language, and how basically we find exactly the same structures there, and how by this coincidence of these structures actually enabled us to do something we would never have expected to even be possible, which is doing NLP on a quantum computer. So NLP is natural language processing. It's something which is now becoming more and more prominent in our lives, but it's incredibly data intensive. So it usually requires a lot of data. People who've seen GPT-3, and I mean, the amount of data is ridiculous. GPT-3, just to be trained, requires something like $12 million in electricity alone, just to be trained. $12 million in electricity alone. So just to represent, to give you the data intensity. Now, so we were able to do something useful on a quantum computer, not competitive, of course, with classical method, but something useful on a quantum computer, while quantum computers are still very small. So that's the big surprise. And the reason that this is actually possible is effectively by this coinciding compositional structure of quantum theory on the one hand, and natural language on the other hand. So that's what I'm going to focus on. And then towards the end of the talk, I'll report on the actual experiments we have been doing. And I was just trying to see who else is in the audience, because there's probably some people in the audience who can actually answer questions. Let me just check who's in the audience. There's probably some people who can actually answer questions in the chat while I'm talking. I think that's one of the big advantages. I see Sarah Zemlich is there. Let me see further. Is there anybody more? I don't think I see anybody more. So there may be some answering in the chat then. Okay, let's start. So I'm giving an historical account on this because it's kind of interesting to see where this came from. And it's also sociology of science a little bit, this story. So around 2008 at Oxford University, actually a little bit earlier, 2005 already, there were three people. One person, Mernou Chadrzadeh, she knew what I would call grammar algebra. So grammar algebra, that's something she knew. I can explain why. So basically, this person is called Jim Lambeck. He unfortunately died a few years ago. Well, he was in his 90s. He lived a beautiful life. And he was at Montreal, and he was a friend of me because I was a postdoc at Montreal around 2000, and I didn't have anywhere to live, so I lived in his house. Now, Jim Lambeck was a world famous ring theory, but he also pioneered grammar algebra. In 1956, he wrote this paper, The Mathematics of Sentence Structure, which completely revolutionized, and these ideas are still in use now when people build parsers and all that, a little bit in an extended form, something which is called CCG. But these things are still used, which come directly from that paper. A very interesting thing about Lambeck is, if you look at the date of this paper, 1956, at least today, and then you see 1999, which is almost 50 years later, he actually kind of changed his own theory. So this thing is called Lambeck grammar typically, what he proposed here. This is called pre-groups now, just to make it really confusing. So this is actually also Lambeck grammar. This is the grammar Lambeck preferred in the later parts of his life, but it's not called Lambeck grammar. This is called Lambeck grammar. So that makes it all very confusing, but it doesn't matter. Anyway, there's a little book from like a couple of years later, which is called From Word to Sentence, and there you can find this theory of pre-groups. which actually substantially simplifies the previous theory. And I'll explain you why these pre-groups are so suitable for us. So at some point, also Mernuge was in Montreal, and then who was a logician, and then Lambeck asked her, can you do pre-group grammar for Persian? Can you work this out? And that's how she learned this grammar algebra historically. So what is this grammar algebra? Let me explain that. This is the case of pre-groups. I'm going to give a very simple presentation of it. Like basically what you got, how this grammar algebra works is you got a collection of basic types. This can be like noun or sentence. So sentence is a basic type. So basic types are things which form sort of monolithic wholes, things which make sense in their own, like a noun makes sense on its own, sentence makes sense on its own. So those are the basic types. And then you got a multiplication, if you want, to make composite types. And you got also, I mean, the name pre-group actually means it's a little bit like a group, but instead of like only one inverse, you got a left and a right inverse. That's really why it's called pre-group. Another slight difference is that there aren't really defining equations, there are defining inequalities. For important reasons I cannot go into, but that's really not that important for what I'm explaining today. So you got this noun type, the sentence type, and then the transitive verb type is of the following form. You got a noun type with -1 on the left, a sentence type with -1, a sentence type, then a noun type again with -1 on the right. What this means is that a verb on its own is not a well-formed entity. It needs on its left a subject, on his right an object in order to form a sentence. And the way this works is if you then stick a noun on the left and a noun on the right, they will cancel out with these inverses, and then in the end you end up with a sentence. And basically this says if I make the composite of a noun and a transitive verb and a noun, then I end up with a well-formed sentence. So that's what this sort of algebra does for you, this pre-group grammar. There's many variations, like there's the Chomsky stuff, which is closely related. There's lots of stuff which is closely related to this, but it is a very simple, easy gadget. Now, what you can do is basically you can think of this calculation, which I just make diagrammatically, because I said like n and -1 n cancel out, and I'm actually depicting here this by this little cup shape. You see, this is the canceling out thing, like a little bit like in Feynman diagrams or something like that. Here, these two cancel out, and this goes through. So I get a little diagrammatic representation of this calculation. Actually, for those who remember my talk from yesterday, and remember I was playing around with these cups and caps, and I said like we've got string diagrams. This little algebraic structure is an example of such string diagram calculus. You wouldn't recognize it immediately, but it's an example. It's a special example. It's a special example in the sense that it doesn't have like black boxes in a sense. It doesn't have the sort of free black boxes because you only have one process between any two types. That's what the lesser equal do. I don't want to go into that. If you want to know about that, I can give you a link to a paper where it's all clearly explained how this is an instance of these diagrams I talked about yesterday. But I mean, you see this, but below this calculation is an illustration of that. You see the cups there and the wire, and really mathematically they are an instance of this diagram structure. They are. So we actually end up with this grammar algebra looking exactly the same as the sort of as the string diagrams for quantum mechanics, which I described before. So that was an interesting observation we made quite early on. Anyway, this is this grammar algebra. I explained to you how it works. So that's what Mernuge knew about. Then there was somebody else, Steve Clark, and he knew about vector space NLP. Now, vector space NLP, pretty much everybody knows about that. I mean, we got like a talk by Dominic Widows about it. And you remember he had been doing this for ages. Well, not many people were doing it. And Steve also came into the game quite early. So basically, for those who don't know what this is really, you've got things with meanings. I'm going to focus on language, but you can do similar things for images and stuff like that. And then you represent meanings of words as vectors in a vector space. There is a number of ways to do that. I'll explain the old-fashioned way, because that's was done at the time, and the moment people do it somewhat differently, but I'll explain you old-fashioned way, because intuitively it's kind of easy to grasp. You pick a bunch of context words. So this can be like words you think are good to relate other things to, and you build a vector space with that. Like you build a vector space, and the basis vector. So it's a vector space with a fixed basis, and the basis vectors, they correspond to context words. They can be names of places. They can be whatever. There can be 1,000. There can be 1,000,000, and then but you use them to actually assign them vectors to every single word in language. How do you do that? You basically look how many times a given word, like yellow or green or bitter or sweet, whatever, appears close to one of the context words in a big piece of text. It's got a humongous piece of text. There's something like the entire internet, whatever, and then you see how many times a word appears in the context, and then you use these counts as coordinates. I mean, you will normalize them then because they're probably huge. You normalize them then or something like that. And the thing you can then do, for example, which was very successful, is if you take these vectors and you want to figure out whether two words are synonymous, for example, it works very well. Like synonymous words would end up with pretty much the same vectors. So if your corpus is big enough. So that's what people do. Now people don't really build these vectors anymore. They train them. So they use machine learning techniques to train them. So that's the new thing. And they call them now vector embeddings. So that's the modern way to do this. Anyway, at the time, this was still this building with counting. And then Steve Bradis was a specialist in that. And then, I mean, I was around too, and you hear the sort of stuff I was building at the time. Like that's what I talked about yesterday. I was building out this theory of categorical quantum mechanics. Right. So say then, Dominic Widows was very nice to also advertise her book yesterday. So basically, I mean, I'm just going to recall briefly what I said yesterday. What we need here is that the main ingredients are like these diagrams, which are processes. There can be states, there can be effects. And now this time today, all my diagrams will go from top to bottom. Will all go from top to bottom. So you got states. So states are like these things without inputs. Effects are these things without outputs. And then you got general processes. And then you can also have these very special states and effects, which are cup-shaped and cap-shaped, like I explained yesterday, and which we already encountered in this grammar algebra. So why am I talking about these three different fields? Because at the time, there was an open problem, and this was actually explained in a paper by Steve Clark and Sullivan and Steve Pullman in 2007. And this basically comes down to this like sort of Frege thing I mentioned yesterday in the context of compositionality. Why are there no dictionaries for sentences? Well, because if we know the grammar and we know the meanings of words, then we typically can actually compute the meaning of the sentence in our head. Something we can do. It's not entirely, I mean, yesterday I was actually to some extent arguing against that because meaning is contextual, but in first order, this is something we do. So the question then boils down, how can we formally combine grammar and meaning? So it's all nice to say that language is compositional, that when we know the meanings of words and we know the structure, we kind of know the meaning of the whole. Like, how do we that? How do we that? So we assume now there is no context dependence, and actually too, that actually worked perfectly well with this system too. It doesn't really matter. Dominic Widows yesterday referred to density matrices. That's how you deal to a great extent with like a context dependency. So, but anyway, so we just wanted a mechanism on how to combine grammar and meaning. There was nothing like that. There was nothing like that for this vector meaning and for this grammatical. And basically the answer was categorical quantum mechanics. So the theory I'd been developing, the diagrams I was talking about yesterday, they exactly do that. They do in a very canonical way. They combine meanings as in vectors and grammar as in these grammar algebras. So let me explain how this works. So that was in this paper. I mean, this is a long version from 2010, but the first paper was in 2008. You see the terms here which match Dominic Widows' talk. He was talking about distributional model of meaning, distributional meaning. So that's exactly what we were talking about. A very interesting point, which is also something Dominic talked about yesterday. He was saying people didn't take this serious, this use of quantum and NLP. those days, and now they actually do, of course. Now they do, of course. So you went from crackpot to visionary. I think that's what he said. So we were trying to avoid any connotation with quantum. I'm now like saying this here explicitly. We use categorical quantum mechanics to unify it. But if you actually look at that paper, we try to completely avoid any reference to quantum because we thought we would effectively be branded crackpots, which is kind of interesting. Then unfortunately, all the popular media, they picked up on our work and they start to call me a quantum linguist and stuff like that. I mean, now it's good. Now it's okay. At that time, it was not always okay. Now it's totally okay. It's totally acceptable that such a thing can exist. Okay, let me sort of explain how this works. So here you see a diagram. Now let's go back to yesterday. How would we interpret this diagram yesterday? In the beginning, kind of forget Bob. Assume Bob is not there, take away Bob and take away this little cup that goes to Bob. So what you actually have there is a bit like a teleportation diagram. You got Alice as the state at Alice's side, then you got Hades as a shared state between Alice and Bob, so to say. I mean, it's a bit confusing because there's now two Alices and Bobs. There's Alice on the boxes and there's also Alice and Bob as in the agents. So then this cap state wire is like the bell measurement you do. This is like the bell state you usually use. And then after the process, Alice's state is at Bob's end. So this looks like a teleportation process. Now, if I bring Bob in the picture again, it's like a double teleportation. I teleport both Alice and Bob through the word Hades. It's like, and so we can think of this whole thing as some sort of sophisticated teleportation process where these are the resource states. You got your two states which you want to teleport. This is like the shared state which enables the teleportation. And then these are sort of the bell measurements which makes you realize the teleportation. So this picture can be completely interpreted physically in terms of teleportation. But on the other hand, it can also be interpreted as a linguistic diagram, purely about language. So you remember this slide where there was my calculation. This is the grammatical structure. Question was how do you combine grammatical structure and meaning? Well, we just take this diagram of this grammatical structure now very seriously. Don't think of it as a calculation, but think of it as an actual physical process. And we stick in not just this grammatical type, but the actual word meanings. So here you got Alice word, you got Hades word vector, you got Bob word vector, and then you apply the grammatical structure to it. So let me go back to these pictures. This is now Alice's vector, Hades' vector, Bob's vector, and then we apply the grammatical structure to it. And what comes out here, we interpret as the meaning of a sentence. Now, it's all good to to declare that. It's one thing to declare that, but then people actually did a lot of experiments with this, and this sort of theory at the time outperformed anything else for the obvious reasons. For the obvious reason, because there wasn't any really competing theory. People did stuff. They, for example, just added up all these vectors, Alice and Hades and Bob, or they multiplied them. They did stuff like that. But there was never sort of a grammar awareness in these mechanisms, and this was sort of the first grammar-aware way of composing these meanings. So it worked well. I mean, and the reason it got picked up was exactly because the experiments were really outperforming everything else around. I mean, now this was pre-machine learning. This was pre the big deep learning boom, I should say at this point. This was before that. Okay, let me now just elaborate a little bit more about this interaction of language and quantum to make you more familiar with that. I'm just going to go through a few examples, and I'm just going to treat them as language and quantum theory are the same. So if you've got a word like black hat, so that's a noun with an adjective, one way to think about it is like hat, and then you apply black. So you modify a state hat, like think of this as a state like a sign, and then you modify it with black, so it turns this state hat into a black hat. That's really how you should think about this picture. You take a hat, which is a vector, and you turn it into black hat by applying some process to it. So this is really how you can read like hat like as black hat as a quantum process. Now, this looks a little bit different from this sort of diagrams. And the reason is, of course, when we speak, we usually put the word side by side. When we write, we put the word side by side. We write like this. So this is our sentence. And so we actually should parallelize this to make it actually look like in the way we speak, because now there's two dimensions. There's like the horizontal dimension, the vertical dimension. We need to get all the words horizontally. How we can do this is by using these cups and caps. You know, I can actually sort of I can unyank this bit of wire between black and head, and now black and head are side by side. And then I actually take this cap and I sort of merge it together with black. This is kind of Choi Jamelkovsky I'm doing here. This is Choi Jamelkovsky I'm doing here. So you end up then with a state which takes this shape, and then let me go back. This thing is really just the Bell effect, like I said yesterday. That's the Bell effect. So we can actually write black hat as state black tensored with state hat, and then Bell effect applied to black. Now it looks completely like a teleportation diagram, right? We use the bells. I mean, actually, this is a logic gate teleportation diagram. Logic gate is something that's also quite old in quantum computing. It's where you do teleportation, but instead of a Bell state here, you use another state. And then the result of this is that this state, whatever map it represents, is in the end applied to this. So this kind of a logic gate teleportation diagram you get here. So that's how you apply an adjective to a noun. And so you can write this in standard notation like this. Let's go for something a little bit more sophisticated. Alice hates Bob. So you could think of this as Alice and Bob, and then you apply a box which sort of makes them hate each other. We change Alice and Bob and turns them into something in a situation where Alice generally hates each other. That's the way you can think about this. Okay, now we can do the same trick. We're gonna try to put 8s in between Alice and Bob by means of cups and caps, and then we absorb the caps in hate, so it actually also becomes a state. It's just like we did before. It's a little bit more sophisticated, and now we end up with this diagram we've seen before. So that's the way to do this from a more quantum mechanical perspective, and then you can write this in ordinary notation. So this is this more sophisticated teleportation I was talking about. So what can you do now? I mean, if you got a sentence like this, because that was the big goal. So I talked before about that when you take these vectors for words, you can use them to compare meanings. You can see which words are synonymous, how closely words are related. So what about sentences? Now we got a meaning of sentences, so we can check out whether sentences actually are closely related, right? And yeah, so how do you do that? Well, you take one sentence, which you see here, and then you take another sentence and its diagram, like the one on top, and then you just compute in the product. So here I've got the sentence, Alice hates Bob. I got another sentence with a completely different diagrammatic structure, by the way, because different grammatical structure. Alice does not like Bob, but we can perfectly compare them. We can perfectly compare them now. So that's the sort of stuff we did. Yeah, you see there's a lot more cups and caps here. I'll go into that later. But so we could then compare meanings of sentences and using this quantum formalism, but we weren't saying this was purely within the context of classical natural language processing. All this stuff, purely in the context of natural language processing. And then, I mean, this was actually a completely new. It was to some extent a new theory about language too, because usually there was like a big separation between people who are thinking about grammatical structure, a la Lambeck, a la Chomsky, and then people who are actually thinking more about meanings. There's one exception, Montague semantic, but the only thing he really did was logical meanings. Everything was true or false. Like when we talk vector space meanings, more sophisticated meaning structures, there wasn't really anything like that. So after we sort of were able to combine these structural aspects, which are in grammar and other thing, and this meaning aspect, we could actually also do some new things. Sometimes there are words in language which are kind of more logical, like a relative pronoun, like that. I mean, you saw some examples here, like does, not, does and not. I mean, you're not really going to assign like empirical vectors to these things, because these vectors, these meanings are typically built empirically. So there are words which you can kind of assign logical meaning to. And so we did some work there. I'm pointing out this paper. I mean, this is a paper which gives like a big overview of a lot of it and does some new stuff. So if you're interested in these things, this is a good first place to read, actually, the mathematics of text structure. Right. So let's look at a sentence with relative pronoun. She who hates Bob. She who hates Bob. What comes out? Okay, this is a mistake. This should be a thin wire, not a thick wire. So that's a typo. So think of this as a thin wire because it's a noun. She who hates Bob is a noun phrase, so what you get out is a noun. And then we thought very hard, so what should who be? What should who be? How should we model who? Look, here are the spiders. Remember the spiders from yesterday, the multi-wires and all that? That turned out to be the right way. I mean, of course, we did experiments with that and all that, and that turned out to be a really good way to model a relative pronoun. So it's not some empirical box, it's some sort of new, so we call this now internal wires. We fill the box with wires, these logical. And actually in recent work, which I'm not going to talk about, but there is a paper on the archive, which is called grammar equations. I could have referred in a paper on the archive from last week or 2 weeks ago called Grammar Equations with Vincent Wang. We come up with a whole zoo of this kind of internal wirings for words. So you can have a look there, grammar equations. But this was a first example, which we already worked with for a long time, which dates back to like maybe 9 years or something. And let me remind you what these spiders are. These spiders are built on a basis. Now we fix a basis. So to some extent, it worked well with this idea that meanings were built on a basis, and we build these things like that. And now basically meanings. So it's kind of interesting because now there is less separation to meaning of and grammar. I would call this is meaning and structure. We shouldn't say meaning and grammar because it's a piece of structure in language which was never considered before because there was simply no way to accommodate something like that, like spider, filling in words with spiders. There was no sort of framework to accommodate that. And now you see that the separation between meaning and grammar is a little bit less. So you can do much more of this stuff here. It's a much more sophisticated sentence, like Bob gives Claire flowers that Alice does not like. And Sarah, can you please post the link to the? So there is an online tool. There's an online tool by Dimitri Karsaklis and Richie Young, where you type in any kind of sentence and it gives you a diagram like this. It doesn't give you these internal wirings in box, but it will give you all the stuff on the bottom. So Sarah will probably, if Sarah's still there, can type the link to this diagram generator because it's a really fun thing to play with. So you type in whatever sentence, whatever complicated, and it gives you this diagram. I should have put this in my talk. Sorry. Now you can go further. So okay, you see these internal wirings here. You can actually go further with them. So what is a verb like gives? We were thinking out what is a verb like gives or like actually really doing? What is actually a verb doing in general in a sentence? Well, a kind of if you got a verb like Alice hates, if you got a sentence like Alice hates Bob, first you start with knowing nothing about Alice and Bob, and then after the sentence, you know that they hate each other. So the verb is sort of almost like entangling Alice and Bob in a certain way, coming from a quantum perspective. First, you got Alice and Bob, you know nothing. Then you kind of entangle Alice and Bob. So you impose something on that. Can we make this explicit in these diagrams, this sort of intuition? Yes, and they actually will become simpler. This will simplify the diagram. So this conceptual thinking simplifies the diagram. It's again something you couldn't really do before because the way people worked with these vectors before, you see, you got a composite type here. You got many hybrids coming out of one thing. Like initially in NLP, all these words, whatever the type was, verb, adjective, transitive verb, adverb, whatever, they all at the same time. They all live in the same space, which is kind of a natural. If you come from computer science, you understand the concept of type, and then you know it's very unnatural that they would live in the same space. So what we did was we figured out that by again using some spiders and by changing this box to this box, so the thick wire now becomes two thin wires, and we stick two spiders in, we could come up with a very elegant presentation of this intuition I was telling you about. So we got Alice hates Bob. Now I stick in these spiders here. I stick in these spiders, right? You see, I stick them in like that. And now I can deform this diagram. I don't know whether you see. I sort of pull these two wires down here. See, and these two dots, like I move them under Alice and Bob respectively. So I can deform this diagram to this diagram. And now it's as if like you got this entangled state hates, which get injected into Alice and Bob. You have to, so I think of this I imagine these dots to be like hands, two little hands. So you got H, and it grabs Alice lifeline, it grabs Bob lifeline. It now sort of imposes this relationship on Alice and Bob. So you got Alice and Bob, and it imposes an H imposes a relationship. Now here is something brilliant. If you do that, then you can do something which was never really part of this sort of grammar algebras. These grammar algebras, they were about sentences, individual sentences, nothing more, just single sentences. But of course, when we speak, we sometimes say more than one sentence, and we can tell a story, and that story can make a meaningful whole. So why can't we compose these sentences? So these things, when we were working with these things, like for example, these things, how do you compose this with another one? You can't, you can just form an inner product. If you take this and the meaning of another sentence, you end up with an inner product. So you can't compose them. Now, moving to this stuff, we can actually compose them. Look, I've got Alice, I impose H on Alice and Bob, and then I have another sentence, Bob likes beer, and you see they can form together in one diagram, and I can actually start building a story now. I can start telling a story. I can also say, whatever, beer, no beer. So I can impose no on beer, and then Bob crying and stuff like that, you know, like, so I can build an whole story. I can build an entire story now with these diagrams, which is cool. Okay, so that's all beautiful. So we basically get a new theory of language using this quantum mechanical intuition. And you see, this starts to look like circuits. You really can start to see like sort of quantum-like circuits here. I mean, this, of course, just think of this as some C0 gate, think of this as some C0 gate, and you see a circuit form arising, which is telling you a story. Right. Now, here is the problem. And this was a problem not only starting here. This problem went back to the beginning when people start to do experiments. These big, okay, these are 10. So if this is a million dimension, a noun, and this is a million dimension, then this is a million times a million, whatever that is. I don't care. So, and I mean, actually, when they were doing experiments, they didn't do it like that. They were actually still doing it like that. So that it's much worse. You got a million and something else, maybe a million times a million, and then it's a number that probably even maybe doesn't have a name. So I mean, here we kind of already simplify stuff, but still, so all these spaces in all these wires are separated by tensor spaces. So if you got a story with like, say 10 actors, then you have a tensor product of 10 million dimensional space. Okay, say 1,000 dimensional spaces, but that's still humongous. You can't do this in a classical computer. So what can you? But okay, I shouldn't actually. Okay, I'm going to skip this. I'm going to get back to that. So here is what you can do. You can just stick it on a quantum computer if they would be around. Now, when Will Zhang, he did a PhD with me. He's now the head of the quantum computing team at Goldman Sachs, which are looking at quantum finance and so on. And really, when we said, yeah, I mean, just stick it on a quantum computer, and this exponential blow up is gone, of course, because it's kind of, if you could. Why did people start thinking about quantum computing in the first place? Why did Feynman start thinking about quantum computing in the first place? Well, he says, if you have to do a computation about a quantum system, some chemical system or whatever, it's going to be exponentially hard on a classical computer because the spaces blow up because of all these tensors and all that. So you should do quantum hardware. Here we're working with a language model, which is actually a quantum model, which takes its meanings and its compositions in just like quantum mechanics does. So exactly the same argument as you have for chemistry or for materials is true here too. It's true here too. And yeah, so but at the time, 2016, I had no idea. I mean, I thought this was still a joke, you know. I thought this was a bit of a joke. This would not. I mean, that at least the first 10 years, nothing like this would even be possible even not in a toy experiment. But okay, we wrote this paper. It was a little bit like a joke. Actually, it was even more like a joke, because I remember Will was finishing his PhD and he needed some of time for writing, and the only grant I had was actually a linguistics grant. And I told Will, okay, I can pay you from that linguistics grant, but you should do something with linguistics. And let's just say that we're going to put all these diagrams, this language diagram on a quantum computer and see what happens. So that was really what happened. Now, we didn't just say, I mean, because that wouldn't wear on the paper, we didn't just say like, okay, let's put this on a quantum computer and you don't have an exponential blow up of your space. We actually also looked at algorithms. And I'll explain now the sort of algorithms we were looking at. This slide generalization of what we were looking at then. So basically, we were doing classification. We were thinking about classification tasks. Like if you got a sentence, then can we figure out whether it's about sports or whether it's about romance or whether it's about politics or whatever. And this is like a search task, very much. It's like a search task. So it turns out you can get some Groover-like speed up if you do this on a quantum computer. So it's a very standard natural language processing task, classifying things like maybe newspapers, articles. And so we got a Groover-like speed up, and you can actually generalize this idea to something like some form of question answering. So these were my diagrams. I mean, this is how I can formulate a question. Like instead of saying Alice hates Bob, I can just make this a black box, really a black box, not like a black box you don't know what's inside. You really don't know what's inside because there's nothing yet inside. So this is a different level of black box. So you say what? So you're asking which would be the best fit here on this question mark for the hating Bob relationship. That's kind of how you should think about this question. What should I stick there to actually what fits there best? And I mean, I could also ask, who does Alice hates, and put something like that, or what is the best thing that represents the relationship between Alice and Bob? These are things. So you can start asking lots of questions like that. I mean, this is a much weirder one. This is closer to the classification task, basically. This is Alice hating Bob. Where does this fit best? Where does this fit best? I mean, this is going to be romance, of course. And you can actually ask the same thing from Bob's perspective. I mean, in this case, in Bob, it would be sadness. In Alice's case, it may be anger, whatever. So now answers. So how do we compute the answers to these questions? We basically close these wires. You have to think. So we basically discard, after we ask this question, we actually discard Alice and Bob, a little bit like in a destructive quantum measurement, when you measure where a photon is. So, and here is an algorithm. So you delete these two, then you just get cups here, and you can blend them back. And this really is just nothing but building a product now. This is in a product. So we can now figuring out what fits best is computing this inner product and maximizing it. That's really, so the thing which fits best this sort of stuff, because this doesn't have inputs and outputs, so it's a number, right? Something that doesn't have inputs and outputs is a number. And then, so you can maximize this inner product here. And that turns out, coming from, I think, I wrote the algorithm somewhere, Wiebe. So okay, I think we've got the name here. Wiebe, Brown, and Lloyd, they have this sort of closest vector algorithm. And this really does exactly what we're asking for here, maximizing this inner product. So you get a Groover-like speed up if you do this. So that's kind of cool. So, I mean, so it means there is really not just space use, but also algorithmic speed up when you try to put these things on a quantum computer. If there were quantum computers, which at that time weren't really very hopeful for in short term. Okay, I'm going to skip that. Well, things have changed a bit. Otherwise, probably this conference would maybe not even be happening. And otherwise, I would definitely not have left my faculty position at Oxford to join a quantum computing conference. So things have actually speeded up a lot more beyond most people's expectation, I think. And yeah, so there are quantum computers around now. And so then we start, there were a few books with but now we actually know what's a few issues with these quantum computers. There's a few issues in general with quantum computing people didn't realize before. Turns out, and that's sort of the common consensus, this may change in the future, that if you try to just take classical data and then store this on a quantum computer, the process of actually getting the classical data encoded in a quantum computer pretty much is going to kill all the speed up you're ever going to get. That seems to be like the current assumption. This may change in the future, but that's currently how things are. So you can't just stick your classical data on a quantum computer. Basically, what you do now these days, everybody is doing is using the variational, like a variational learning. You use your circuits as sort of variational circuits, a little bit like neural networks, and you're going to train the variables of your circuits, which are certain gate settings, and that's how you're going to encode the data. So basically, I mean, I'll explain now later how we do this exactly, but it's like we're like going to train the diagram, the boxes in the diagram, to get the right meanings on the quantum computer, rather than actually sticking the data in the quantum computer directly. And so this is what we described here. And then we also actually made some other improvements on how we could actually do an actual experiment on existing quantum computers. I think, so this paper actually basically was sort of proof of concept that it can be done. Then this is a much longer paper, which goes much more in the foundations. So this is also a good place to start reading about this quantum natural language processing. And really, okay, I'll explain now what I was saying before I will do this training. So in this paper, we basically use the ZX calculus, which I talked about yesterday. So these are spiders for two different bases. So here you got spiders from the 0-1 basis, you got spiders from the plus-minus basis. These are two states which I will be using too. And so how do you make this into a quantum circuit? So this is almost a circuit, but it's not a quantum circuit now. You basically do this. You pull out two X spiders. You just pull out two X spiders. These spiders would fuse together and just get you back there. But what I get now is I've got these like horizontal things here, which, as I said yesterday, are C0 gates. So I've got now the meaning of Alice, the meaning of H, the meaning of Bob as states. I apply C0 gate there, I apply C0 gate there. Then I do this sort of this post-selected effect. I mean, this is expensive, but you can get around that. This is just for demonstrative purposes, I'll tell you that now. And actually, you can already get rid of one by, for example, doing this. So I turn this state into a process. And now, of course, so this is like a quantum circuit that, I mean, there's still some variables here. So I'll tell you how to deal with this just in a second. So this is now a quantum circuit which encodes these sort of language diagrams. And the next thing to do is like to parameterize all these things which are in here. I've got these boxes, and you can, this is like, just for, if you think of them as being qubit states, this is like a sort of universal parameterization. So this is full parameterization of the previous one. So now I've got so these are phase gates. I've got C0 gates here. I've got phase gates. So now I've got something I can stick on a quantum computer representing language. It's like, and so we use the ZX calculus here in a fundamental way to deform these diagrams. So this is actually also an important application of the ZX calculus here. Okay. So basically, so to summarize, you take a language diagram like that, and what I've been showing you is how you actually turn this into something that is recognizable by a current quantum computer. An important something that has sort of these variable phases here. I think Jacob Biamonte talked about variational circuits a few days ago. This is really what you got now. You've got a circuit with variables that you can train. And so we did that on quantum IBM quantum hardware. You find the description of these first experiments in this paper. And yeah, so basically the way you do that is you have some initial setting of your variables, then you do some measurements. Now, what do you measure? This is supposed to be a sentence. So what we did is we took a bunch of training sentences, which were sentences we assumed to be true. Sentences we assumed to be true. So we did some variable settings we picked some initial variable settings, we measured them, and then we see whether the measurement data really matched what we expect them to be. Or maybe they had to be false, or maybe they had to be true. And then we just use a classical optimizer, we readjust the settings. And we do this over and over and over. So we're actually training the circuit so that the meanings of the words get encoded there. So this is actually a much more modern way to come up with the meanings, in contrast to what I was talking about earlier, where you do these counts. So this is really using machine learning to actually train the meanings, giving some context. This is also what I was talking about yesterday, that the meaning doesn't come bottom up. but that like from the meaning of the whole, you can actually deduce the meaning of the parts. That's exactly what we're doing here. We assume that we know the meaning of these sentences as a whole, and from that we derive the meanings of the gates. So we're actually here doing exactly this new notion of compositionality I was talking about yesterday. Top down, the meanings come from the whole, and then you train them on the parts. So and we actually train them in a grammar-aware way. So these meanings are now being trained within full sentence structure, where the grammar is actually part of when we are training things. There is a nice paper by I think Alexis Toomey and then Coecke, I can't remember the other name, maybe Alex Coecke, on the general principle, categorical principle of this top-down learning. I think the paper is called Vectorial Learning. It's on the archive. It's just like in proposal stage, but it's a really nice idea which goes beyond like what people usually do in deep learning, taking much more structure into account. Anyway, so that's the training thing we did. I mean, here this is just a graph, because basically the main question is, does this training converge? Does this training converge to something? And then actually also the next thing, once we train this circuit, we are actually asking questions, just like I described before, the question answering. And so there's two things. Does the training converge? Do you get the answers you expect? Those are the two questions you have. And it all worked out very nicely. The training converged, and then it matched what you actually expect from a classical simulation. So that's nice. Then what we did is, so the first one was sort of small proof of concept experiment. Then we say, let's go to what NLP people call mid-scale. So let's scale up things. And so we did the experiment also with a corpus of like more than 100 sentences, and it still kind of worked nice out. So things are scaling up, and we're still pushing further and further at the experimental side now. So yeah, this thing is a real thing now. This quantum processes on processing natural language on a quantum computer is a real thing, and it comes with both algorithmic promise and the fact that basically the spaces become so big that you essentially need to do it on a quantum computer. Right. So let me sort of go to a summary of what are the big upshots of this story of doing a natural language on a quantum computer. Right. Well, first of all, that was the first thing I said, it is quantum native. We basically use a model which combines meaning and grammar. Now, let me go back, because there was some slide I skipped. You can't even, what I'm going to say now, you can't even read about in any papers. Where did I say this? I think here. Here, yes. What I've said, because we're still writing this down, but something we only realized recently is that if we move from this sort of diagrams to this sort of diagrams, things become actually a lot simpler. Like the structure of a very complex sentences with lots of cups and cups and cups becomes actually much simpler. How does this happen? Where does the magic come from? So what actually happens, and there's still some things we need to understand better, is but by going by the circuits, we're actually eliminating language-dependent features like word order. So in different languages, you've got different word orders for say, object, subject, and verb. Pretty much any permutation of those three happens in some language. So all that stuff is gone when you go to these circuits. Lots of language-dependent bureaucracy is gone. It turns out that language wants to live in two dimensions, but we poor humans, we can only speak linear word after word. That's why we had to make language actually a lot more complicated than it actually wants to be. These circuits are very much simplified forms of language. In modern machine learning, people have been discovering that like this complex form of grammar is actually almost too difficult to encode, taking into account how people actually speak. Now, this simple, much more simple form of language is actually much more natural and native to encode and mix up with like machine learning techniques. So even classically, I think this circuit form is going to give us a big advantage. And so we're doing experiments with that also classically now. So anyway, that's something I wanted to say at this point. So just to qualify that when I say, where was I? quantum native, that with what combines grammar and meaning, this is not grammar in the strict sense anymore. This is really a very minimal interaction structure in words, much simpler than grammatical structure. That's really what we do when we pass to the circuits. I probably should have changed the slide there. Okay, NISC native, like this grammatical structure classically was exponentially expansive. Now, the only way people are now encoding stuff on a quantum computer is using these circuits, using these variational circuits. So they're kind of part of the setup. So we don't have to pay for them. We don't have to pay for that grammatical structure because the circuits are really part of the setup on how you actually get data on a quantum computer by encoding it as these gate settings. So it's kind of coming for free. So what was classically exponentially expansive, the encoding these structures actually now comes for free, which is a pretty cool thing. So that's what I mean by NISC native. And so from a QML perspective, people make ansatz, like picking the structure is something people call ansatz, and then they basically pick them in terms of the work the best. For us, these ansatz, quantum machine learning ansatz, are actually a meaningful thing. This exactly is how these words interact with each other in language. So they are not just any circuit, they're exactly doing something very meaningful. So it's a tensor network, so it's an expansive thing, but it explains how these things interact, and they're just part of the setup of the quantum computer. So of course, this passage from this diagram to this circuit implementation couldn't have happened without stuff like first of all, the matchup of language with quantum could not have happened without a diagrammatic formalism, because that's where they meet. That's where they meet. Then turning this diagram on the left in this diagram on the right fundamentally relies on something like ZX calculus, where you break up stuff in little pieces, like Z. So it's fundamental. So the diagram stuff is totally fundamental here. So I gave the example. So we can actually move from single sentences to text, which is really cool. And this actually goes hand in hand with the circuit form. So we got speed up. We got speed up from the paper of Will Zhang. Now, sometimes people say, is this good enough? Is this good enough? I mean, if you say quantum native, then and you think, well, that's like chemistry simulation. Can't you do your algorithms more inspired by what people do in chemistry? Yes, you can. I mean, it's something we're working on now. But so what we think of is like we think of language as an evolution, as a piece of text like this as an evolution, and then maybe we want to learn something about that evolution, just like exactly what people are trying to do in chemistry, trying to learn something about a chemical thing, and that so we're basically now looking for algorithms, meaningful algorithms that are 100%, which are sort of in the category of the chemistry and the materials type of algorithms, because this is what you want to do with this language, because it is like an evolution. So I mean, we haven't written that down yet, but this is making good progress. So this is going to give us a much more compelling kind of speed ups than just Groover-like speed ups. How am I doing with time? I mean, okay. So let me conclude. I'm not going to talk about that. So we were just talking before about. We mainly talked about linguistic grammatical structure here, but there's much more things which you can actually naturally encode in the structure and these diagrams I say. For example, I mean, I already mentioned, for example, narrative, where you actually have a certain context. We kind of know how to bring that in. Physical space aware, like if you do general AI, I mean, machine learning doesn't do it, but like traditional in robotics, you really need your robots to have some sort of embodiment in real space. So if you want to actually go towards general AI, like artificial general intelligence, they say, then you actually have to give your AI a body. And so we can combine everything which I'm talking about actually with physical space, our senses, and like also an important thing is like usually AI is very static. I mean, you train your system, and that's the end of it. Like GPT-3 doesn't know COVID happened. For example, the setup of our model, actually meanings get updated all the time. So it's sort of an update model of language, and that makes it very different too. And all that stuff needs to be, is I think, necessary if you want to go beyond the sort of black box stupidity of, I mean, these are not my words, modern AI. This is from like the Google AI leader. Like, you know, AI is very, very stupid, at least compared to humans. So if you want to go a little bit further, then all these sort of features need to be brought in. That we take AI seriously is that actually Steve Clark, who this story started with, if you remember, has now joined Cambridge Quantum Computing from DeepMind, where he was the last couple of years, to actually basically is now the head of AI at Cambridge Quantum Computing. So we're taking this AI thing very serious, both quantum and also classical. But quantum is kind of the way forward in the long term, I think. I think that's all I had to say, right? So again, like, I post about this stuff a lot on Twitter, if you're interested. That's the end of the talk.
All right. Thank you, Bob, for the comprehensive talk. My question is, I wish in especially voice processing, is there such remarkable facts or remarkable works in modeling accents, a complex challenging on them, I wish.
Can you say again, because there's just an ambulance driving past here, sorry.
No problem. My question is that, is there any alternative or similar works in voice processing, in accents processing, and modeling the model files for accents in NLP?
Oh, so you're talking about accents?
Yes.
Dialects and things like that. I mean, there is a different area which is phonetics, which takes care of these things. This is
Yes.
There's many different components to this natural language processing. Of course, like you want to train, like NLP, things like Alexa now, they're supposed to actually be trained on your accent. I mean, in my case, it's completely hopeless. Like they don't understand me at all. But it's sort of part of the sort of pipeline. It's very much at the beginning of the pipeline that you actually want to identify the phonetics in natural language. We're of course nowhere near there. Like in our pipeline, we start mainly with written text. And then we do parsing to get the grammatical structure, and that's actually the tool I think Sarah put the link for, and then it goes to the classical optimizer and the quantum computer. That's kind of our pipeline.
Yes, I understand. And especially in continuous languages, for example, especially in Persian, it's very hard job to parse the sentences and grammatical errors.
In Persian,
prepare the errors grammatically.
You say Persian?
Yes, Persian.
Yes, actually, there is a paper by a Persian team who actually followed up on our things and then specifically started to develop theory taking into account Persian. There is a paper from like a few months ago on like quantum natural language processing for Persian specifically. Now, you know why Persian is a very interesting example for me is like this stuff, this quantum natural language processing becomes more and more sort of needed when the sort of interactions between words stretch very far. And in English and most Western languages, the interactions between words are quite close. You see in this example I've got here on the top of my slide, it's almost nearest neighbors interactions. In Persian, the interactions go very far.
Yes, yes.
They go very far.
It's more continuous.
Yeah, and that actually probably makes the need for something like this higher even. There's a nice paper by the grammatical structure of Persian compared to Arab and compared to Hebrew and compared to Western languages by Marunish Adrzadeh, but I think it's in the pre-group of Persian. It's a paper like pre-group analysis of Persian or something. And there you really see these big distances in Persian poetry. I think she did Omar Khayyam.
Omar Khayyam, yes, actually. And we have any other poetries like this, and maybe I can present one of them for you, if you wish.
That would be nice, yes.
Yes, actually, yes. Maybe it's from Fakhruddin Araqi. He says that همه آهوان صحرا سر خود گرفته بر کف به خیال آنکه روزی به شکار خواهی آمد. It's dedicated to you.
Okay, that's very nice.
Thank you, all the guys. Any other question, please?
You know, my Persian is quite limited to animal names and swearing, but I know a few.
Yes, yes.
I know a few
Maybe the
Persian.
wine also.
I would actually like to know how is this all applied to the Chinese language? Because Chinese language doesn't have you know, like alphabets; they have characters put together. And
I can't comment on this, but I mean, I don't know whether Vincent Wang is online, because he or Vincent Wang or Quan Long Wang, they could comment on this much better than me. But I mean, they confirm me that it's all work for Chinese. I know nothing about Chinese. I know some Persian words, but I know not a single Chinese word. Okay. But I don't know whether Vincent is here but he is. But it's supposed to all work. Kwang Long Wang, Vincent Wang, so we got quite a number of Chinese people working in the team here. Mm-hmm. So that all I can do is they say, yeah, it works.
Okay. Thank you.
Thank you, Bob. Any other question, guys? I can see the chats. Okay, it seems that there is no question. And thank you, Bob, for the comprehensive talk.
Thank you for setting everything up. Hopefully next time we are in Iran and I can use my Iranian swearing.
Absolutely, absolutely. We wait here for you. Thank you. Thank you.
Thank you.
Thank you.